All right, we're dealing with a new topic in trigonometry called inverse circular functions. We're going to be looking at the graphs of inverse trig functions like the inverse sine, inverse cosine, inverse tangent, and so forth. Now we call them inverse circular functions, and we're going to be looking at their graphs and some of the properties of the functions themselves: domain, the range, the intercepts, different function values, how to calculate them, both by hand and with a calculator, and some other interesting features, some symmetries and other things. So all that stuff is incorporated here into this section, so it might be a little bit longer section, but we'll kind of identify really 6 different graphs: one for the inverse sine, inverse cosine, inverse tangent, and then the inverse cosecant, secant, and cotangent as well. A little bit of background too, before we get into that, dealing with the inverse function in general, just a general idea for an inverse function. You've probably seen these in your algebra courses before, but if you had, let's say you had a function, and we'll talk about some algebraic functions here for a moment, like the function x cubed for a moment. All right, x to the 3rd power. Well, that function has an inverse, right? To find an inverse, you replace the f of x with a y. You interchange the variables because inverses essentially reverse the inputs and outputs, okay? So they reverse the inputs and outputs. So you would switch the variables, the inputs and the outputs, and then you solve for the y. Well, here you would take the cube root of the x, and so the inverse function is the cube root of x, which makes sense because cube roots undo cubes and cubes undo cube roots, and so they're inverses of each other, okay? Their inputs and outputs are switched. In fact, every ordered pair that's on the graph of one function will be reversed on the graph of the other. Okay, for an instance, with this one, if you did f of 2, 2 cubed is equal to 8. So the point, or the ordered pair, 2 comma 8 is on the graph of x cubed. With the cube root of x, you invert the order of those 2 points. And so we would say f inverse of 8 is equal to the cube root of 8, which is 2. All right, and so that tells us that the point 8 comma 2 is on the graph of the inverse, the cube root. So we have 2 comma 8 and 8 comma 2 on the 2 different graphs. In fact, with any function and its inverse, the ordered pairs on one will flip when you plot them on the other function, okay? The inputs and outputs switch. As a result, the domain and the range switch, right? The domain is the all the values of x, and the range are all the values of y. Domain are the inputs, the range are the outputs. And so if you're switching all your ordered pairs, all the inputs and outputs, then your domain and range switch as well. So the domain of one function will be the range for the other, and the range for the one is the domain for the other, okay? So they switch. Your intercepts switch. Your x-intercepts become your y-intercepts, and your y-intercepts become your x-intercepts, okay? So it's all back and forth. Your x's and y's all switch. What's also interesting is that the graphs switch in a weird way. They end up being a reflection. If I were to plot the graph of these 2 particular functions, x cubed is a graph that kind of looks like half of a parabola, right? It kind of has this curve going out, but it also has one going down to the left. So it kind of snakes its way, from negative infinity up to positive infinity. Well, the graph, so this is the graph of f of x. The inverse, which is the cube root, does something similar, but it kind of starts to the left and goes up and out to the right. The cube root doesn't increase as quickly. In fact, what you end up with, maybe I'll dash this one in. It's a graph that kind of snakes its way from left to right. Both of these functions have all real number domains and all real number ranges. They extend indefinitely in both directions. But what's really interesting is you can see sort of a mirroring image between them. In fact, the mirror, or the symmetry line, is the line y equals x. It's the line that runs on a 45-degree angle through the first and fourth quadrants. Right, and so that line is the line of reflection for any point from one graph to the other. Okay? When you interchange the coordinates of from one graph, they reflect across the line y equals x, and then end up on the graph of the other, the inverse. The line y equals x is a line with a slope of 1 and a y-intercept of 0, right? Y equals 1x plus 0, if you think of it in slope-intercept form. All right, so this is just a quick rundown of some of the review ideas, or the foundational ideas for inverse functions. We can find inverse functions for a variety of different types of functions. The x cubed is a good example. Linear functions, for instance, have inverse functions. But there are some functions that don't. An example of a function that does not have an inverse is the x squared function, a parabola, right? This one doesn't have an inverse because when you reflect it across the line y equals x, if I were to sketch that in here, and I'm doing this very rough, right? I'm not giving a lot of detail. But if you reflect a parabola across the line y equals x, you get a parabola that opens on its side. Opens to the right. Well, the problem is that graph is not a function because it fails the vertical line test, right? You can draw a line, a vertical line through the graph, it hits more than once. So this is not a function. Okay, and so when you have a failed vertical line test, it comes from the fact that the original graph fails what we call the horizontal line test. These 2 points that are vertical from each other on the inverse, or on what would be the inverse, are horizontal to each other on the original function, right? And so the original function fails what we call the horizontal line test. And if it fails a horizontal line test, it is not what we call a one-to-one function. One-to-one functions are the only functions that we can have inverses for. The x cubed function is one-to-one because this original function that I plotted, or the original graph, passes the horizontal line test. Every horizontal line hits the graph once, or 0 times, that could be 0. Okay, but with x squared, it fails the horizontal line test, so it doesn't have an inverse. There's an inverse graph, but it's not an inverse function. What we want are inverse functions here. We really want a single output for every input. Otherwise, we get confused. When you plug stuff in, you've got multiple options of things that you could get out. We don't want to have to choose. And so we want things to be functions. Okay, so that being said, there are some ways to tweak this example to make it one-to-one. Okay, so we'd say, let me write a couple definitions up here before I show you the tweak, and then I'll come back to that. I'm jumping ahead here. So I would say that one-to-one functions pass the horizontal line test. I'll abbreviate that, HLT. Just means that for every output, there's a unique input, right? Or I'm sorry. Yeah. For every output, there's a unique input. All right. So you can't have two output, or you can't have the same output coming from two unique inputs. If you have an output, it has to come from a unique input, right? So one-to-one functions pass the horizontal line test, and only one-to-one functions, I'll abbreviate one-to-one as 1-1 there. Only one-to-one functions have, oh my handwriting is terrible, have inverse functions. Okay? Only one-to-one functions can have inverse functions. And so that's what we're going to deal with. Now, like I said, the tweak. There's a way to tweak this so that it can be one-to-one. And the tweak is that we can restrict the domain. We can still work with the x squared, the x squared function, but we have to write it so that we are restricting part of the graph to be a one-to-one portion. So if you said x squared, where x is greater than or equal to 0. So now I've just established a new domain. Instead of having an all real number domain, I'm just going to take half of the graph. Well, this graph is just the right half of the parabola starting at the origin, right? That's a one-to-one function because it passes a horizontal line test. And so it has an inverse function, namely the square root, right? So the inverse, so this is f of x, then f inverse is the square root of x. And what's neat about this is that, again, the domains and the ranges switch places. Well, I guess both of them, both the domain and the range are from 0 to infinity on both functions, but they do switch places. And of course, they are reflected across the line y equals x again. All right. So we can have some inverses. In fact, if we wanted the other side of the parabola, we could create the function for that as well. We could say that, you know, if f of x equals the square root of x, x squared, where x is less than or equal to 0, that gives us the left side of the graph. Well, then the inverse would be the square root, the negative square root of x. Okay, the negative square root of x starts at the origin and comes down to the right. Right, so that would give us the inverse, the reflected graph across the line y equals x. Here's y equals x, and each point would then reflect across that line to another point on the other graph. Yeah, that wasn't drawn very perpendicular, but it would be perpendicular. Okay, now this one's an even better example because this one you can see the domain and range switch. For f of x, the domain is all the negative numbers and 0, right? It's everything to the left. So it's negative infinity to 0. Whereas the range, well, when you take something and square it, it's either going to be 0 to infinity or 0 and positive. So the range would be 0 to infinity. With the inverse function, it's the opposite, right? You can only plug positives or 0 into a root. So here, the domain would be 0 to infinity, because those are the only things you can plug into that square root. The outputs are all negative, right, or 0, because you're taking the principal root and multiplying by a negative. So the range would be negative infinity to 0. And now you can see how they switch, right? The domain and the range switch places on the inverse. Kind of interesting. Okay, well, we're going to apply this same logic to trig functions. And the way that we're going to do that is we're going to restrict the domain of our trig functions so that we have one-to-one functions. And we'll start with the sine for a moment. And we'll show you the cosine and the tangent. And the cosecant, secant, cotangent. We'll show all of them. So let's take a look at f of x equals the sine of x. Well, we know that the sine of x is an infinitely repeating wave left to right. And it starts at the origin. You could say it starts at the origin, but where it starts, you know, it's indefinite in both ends. From the origin, you go up, then down, then up, and so on. And then to the left, you would go down, and then up, and then down, and so on, right? So you have this graph. But this is clearly not one-to-one. It definitely fails the horizontal line test. In fact, the x-axis alone has multiple inputs that result in the same output. We don't want that for an inverse. We've got to restrict this. We've got to narrow this down so that it is a one-to-one function, but yet covers all of the possible outputs, okay? So we need to cover everything from -1 to 1 as an output, but restrict the domain down. Obviously, we can't have all the domain values. So if we restrict this down, there's a couple options. You can't really start at 0 and get a one-to-one function and still incorporate all the range values, all the outputs, because if you start at 0, you go up and then back down again, you're going to create a failed horizontal line test. So what we have to do is actually start to the left and end at the max. So we start at the min, end at the max. This would be starting at -π/2 and ending at π/2. If we restrict the domain to that interval, we'll create a one-to-one function that does include the entire range of values for the sine. So what we're going to do is we're going to change this from -π/2 less than or equal to x, which is less than or equal to π/2. That's our restricted domain, okay? And when we do that, you're going to see a nice curve. Get this drawn up here. So it starts at -π/2 and -1 goes up through the origin and ends at π/2, 1. Okay? So that's a nice one-to-one function. It does incorporate the entire range of the sine from -1 to 1. And you know, we've got nice values here. We could have chosen to go from π/2 to 3π/2 or some other interval, but this one just seems to be nice. It includes the origin. It's centered nicely. It's got some symmetry to it. So this is the one we choose. This is our definition. And now from this, if I invert the sine, I'm going to get what we call the arc sine. Okay, so this is a new function now. I'm going to put this in another color. So f inverse of x is called the inverse sine of x, or we sometimes call it the arc sine, A-R-C-S-I-N. Why, I don't know. I should look that up sometime. Inverse sine, arc sine, they mean the same thing. So we will use them interchangeably, and you'll see them in your book. You'll see them on my math lab used interchangeably. Same thing with the inverse cosine and the arc cosine, inverse tangent, arc tangent, and so forth. This arc word, or prefix, I guess, means the inverse, okay? Okay, so those two things basically mean the same thing. They're interchangeable. All right, now on this inverse function, you're going to take the point -π/2, 1, and you're going to interchange the two coordinates. So it's going to be -1, π/2, -π/2. So I feel like the scale is off on this, which it is. That's okay. Okay, I should probably be careful here. Maybe I should redraw this. The reason my scale is important here is because the distances, in order to get a good graph, a good grasp of what's going on, I really should have the same distance between my tick marks on each axis. So the scale is the same essentially, but the problem is pi over 2, think of it as a decimal, 3.14 over 2 is approximately, what's that? 3.14, 1.6, no, 1.52 or something. It's 1.5 something, right? 1.56, 1.56, I don't know. I'm losing it here. Anyway, so this is over 1, this is 1.5, this is 1. I should probably shrink that 1, otherwise this really isn't going to reflect properly. It's not going to be obvious. So, it's tempting to cut the video right now and edit this and then fix it, but you know what, it's probably good for you guys to see that I made not a mistake, but just need to make a change, and maybe it'll help help the understanding there. So anyway, this is roughly 1.5, negative 1.5, and roughly 1.5, right? Pi over 2, 3.14 over 2 is just over 1.5. So I should probably get a scale. If that's the case, then negative 1, and it's probably a little further to the right. Negative 1 is probably right about there, and positive 1 is probably right about there. So, they're each about 2/3 of the way over. So now I got to get the same scale going down. So let's say right about here is negative 1, and right about here is 1. That's about the same distance, pretty close. Okay, so that will help then to make this graph look better. So let's go from negative pi over 2 comma negative 1 to pi over 2 comma 1. That's my original sign. Okay, something like that. That's the original sign. Then the inverse should be at negative 1 comma negative pi over 2. So let me draw this in with another color. The negative pi over 2 and pi over 2 should be right around 1.5 and negative 1.5, just a little bit over that. And then the graph is going to be at negative 1 comma negative pi over 2 and 1 comma pi over 2. And the curve is again going to be a reflection across the line y equals x. So it's going to sort of come up, go through, and up again. So that green dashed graph, or maybe I'll even make it solid, that green graph is going to be the inverse sine, the graph of the inverse sine. Okay, all right, that's good. Okay. So on the original sign, we had the endpoints are negative pi over 2 comma negative 1 and pi over 2 comma 1. On the inverse sign, the endpoints are negative 1 comma negative pi over 2. So you just interchange the two coordinates. And up here you'd have 1 comma pi over 2. Again, interchanging the coordinates. Okay, so now we look at the domains and the ranges of each. For the original sign, we've restricted the domain. So the domain is from negative pi over 2 to pi over 2. The range is from negative 1 to 1. That hasn't changed. The range is the same as it normally would be. For the inverse sign, however, we interchange those, right? We flip the domain and the range. Notice here with the green graph, the domain runs from negative 1 to 1, and the range from negative pi over 2 to pi over 2. So we'd have, for this one, a domain from negative 1 to 1, and a range from negative pi over 2 to pi over 2. Now this is really, really important, okay? The range being from negative pi over 2 to pi over 2. What that tells us is that the output for the inverse sine can only be in the fourth and first quadrants. Think about this interval. Values of x between negative pi over 2 and pi over 2 are in the first and the fourth quadrants. If you can see, if you can imagine where my arm is, the axes there. I'm going to throw my shoulder out doing that one. Anyway, so that's your range, okay? So the outputs are only in quadrants 1 and 4. Furthermore, they're not only in 1 and 4, but the fourth quadrant angles are negative rather than being all the way around between 270 and 360, or 3 pi over 2 and 2 pi, right? So instead of being the positive version, you have the negative version. So when you go to your calculator to try to find some of these inverse sine values, the outputs are always, from your calculator, are always going to be in one of those two quadrants with positive angles in the first quadrant and negative angles in the fourth quadrant. It's often the case that we don't really want the negative fourth quadrant angles. We may want the positive fourth quadrant angles. Or perhaps we want an angle in the second or third quadrant. And so we've got to be careful that whatever we get out of the calculator, we need to convert after the fact to get the angle in the correct quadrant that the problem requires. Okay, so that's going to be an important part moving forward. For right now, it's just a note, but it's something that I'm going to be coming back to regularly. Okay, I think we'll move on to the next video to address the cosine and the tangent, some of the other trig functions from there.